The data assimilation topic has come up before a couple of times. We will revisit here just to come back in the end to say that data assimilation also affects the reliability and skill of probabilistic or ensemble forecasts. It seems obvious, but maybe we should just re-emphasize it. Okay, so this is just showing the schematic of the numerical weather prediction process followed at the ECMWF, European Center for Medium Range Weather Forecasting, which is in Reading, but because of Brexit it probably will move to Italy or something, to generate a global forecast. So every day there are a couple of 100 million data points that come into the data assimilation system. So these are approximately 20 million observations. So let's say every 6 a.m. the model is beginning to integrate the weather forecast for the next few days. Then overnight all the data is gathered from all sources, which include airborne measurements, ships, weather balloons, radiosondes, radars, satellites, and so on. Some quality control is done, and then they are chosen for data assimilation to generate initial conditions. Typically, numerical weather prediction process initializes only the atmosphere because the ocean sea surface temperatures are prescribed. Some models run the land processes because land has lower heat capacity and can have strong diurnal cycle and so on. You want to represent processes that affect weather evolution, and ocean is considered such a low frequency forcing or varying so slowly that it doesn't affect weather for the next few days. Okay, that's why it is an initial value problem. So here initial conditions are generated by merging data with the model, which is what we call data assimilation. We mentioned sequential methods like Kalman filter and variational methods like 3D VAR or 4D VAR. In 3D VAR, the error covariances do not evolve in time, and in 4D VAR, we take observations along the forecast and we do corrections. As we saw, there is a corrected forecast. It's very expensive but very accurate, and so on. The atmosphere is divided into about 1 billion cells, each having associated parameters such as temperature, pressure, and wind direction. Okay, and the model integration happens from these initial conditions, solving the energy, momentum, thermodynamic equation, continuity equation, and so on. That's what we call laws of physics. Also there is microphysics involved, so there is a dynamic core which solves these, and then there are different parameterizations for convection and so on and so forth. Various things may be prescribed like aerosols and chemistry of the atmosphere, for example, which are considered external forcing in this context, where only atmosphere is producing the internal variability from these initial conditions. Okay, so you get intermediate results, and then you often do the next model step without reinitializing. So you have initial condition at 6 a.m. One morning, you integrate for 6 hours, and then you archive intermediate results and issue 6-hourly forecasts, and then integrate it forward for 12 hours, 18 hours, and so on. So it depends on the data assimilation frequency. So the intermediate results may at some point also go back as the first guess to the next step of data assimilation to generate new initial conditions for further model integration. Okay, so all these depend on individual model configuration, individual choices at operational centers, and so on and so forth. Okay, so that's what is the basic role of data assimilation. The data, here we are looking at synoptic observations, ship observations, and meteorological stations, and so on. So you can see the numbers seem impressive, but you can see there are huge gaps on the ocean. So you have higher coverage here in terms of ship traffic, much lower coverage here, big hole here, lot of holes in the Southern Ocean. So if you are running a global model laws of physics, and you are only having information being used for initialization over land and over the northern hemisphere, and over certain continents like Europe and US are heavily covered. India is doing well, but lots of holes here, and so on and so forth. All these things affect your global integrations, and hence model skills vary, right? And specific predictability of the signal itself may be different depending on the region. Tropics are generally less predictable for weather timescales because of the convection that happens very quickly, and so on. So there are drifters in the ocean, and there are moored buoys in the ocean, which you can go online and find. There are moored buoys in the Indian, Pacific, and Atlantic Oceans. The Pacific has the longest history. More recently, Atlantic came first, and then the Indian Ocean. So even though it looks like an impressive number of observations, as we said, the distribution and time resolution and so on are still something that are being improved. This is showing satellite coverage. So here you have geostationary and all types of satellites going in here. I won't go into the names, but you can see how each one is covering a different region. So you can see geostationary means they focus on their own region, so it's in a geosynchronous orbit. And the polar satellites cover the globe, so they have an orbit that goes around as the Earth moves. They cover the entire globe. So you can see these satellite data also come in. So here we have atmospheric motion vectors from stationary satellites, geostationary, advanced microwave soundings. When we say microwave, it can see through the clouds, it can measure certain things like water vapor, could be better for rainfall, and then there are polar orbiting satellites and so on and so forth. So altogether, this is the example of observation errors used in ACMWF assimilation procedure for some variables. So you have observations either from satellites, radio sondes, balloons, ships, whatever. Each time you have to have some estimate of errors in the observations themselves. For example, if you are using sea level and its accuracy is about average 1 centimeter, let's say, in terms of the sea level variability, but you have to have an estimate of the error, which can be temporally dependent and spatially dependent as well. Often there are models needed to also match observational space to the model space. They are not always the same. Okay, for example, sea level is a diagnostic variable in many models, and sea level observed has to be converted into that model space in terms of vertical projections onto temperature and salinity, because that determines the density and the sea level variability and so on. So all sorts of details are involved. So here we are looking at zonal and meridional wind component observations in meter per second, height observations, so here it's typically geopotential height, and temperature observations in Kelvin. And here are the various height levels going from the surface, hectopascal 1000, 850 hectopascal, up to the upper atmosphere at 50. So the model doesn't resolve the complete stratosphere, which we talked about, stratosphere troposphere coupling, and its impact on things like MJOs. So those are relevant for how well the model represents the stratosphere and how it does the stratosphere troposphere coupling, for example, and how it is initialized in the forecast in this context of data assimilation. So available observations matter as well, which is seen here in terms of the temporal and so let's see, make sure here, column 2 to 4, prescribed RMS errors for zonal and meridional wind components for 3 types of observations at 7 different heights. So used in ECMWF data assimilation procedure. Here we are looking at 2 to 4, we are looking at height observations from synoptic and satellites. So these are satellite observations, synoptic observations. So the errors prescribed in time and temperature are synoptic temp and pilot are types of reports of stations, station observations. So these are, station observations. And these are satellite observations, and AirEp report is airplane observations here. Okay, so these are the errors: 1.8 meter per second, and in the upper atmosphere it increases to 2 meter per second. For the satellite observations, it starts at 2 and goes up to 5 meter per second. In synoptic observations, it goes down from 3 meter per second at the surface because of friction and other errors. Observing system itself may decide what is the error at the surface and at height. So this is doing better at into the stratosphere. Okay, so for height also you can see increases with height here in terms of manual and auto land observations at synoptic timescales, and temperatures doesn't vary that much, but you can see that synoptic land observations have. So there are ways in which these error values are determined, and they are not necessarily fixed in time, but it depends also on the sophistication of the assimilation system in terms of whether these errors are fixed in time during the assimilation and forecast, or whether they vary. So there are many details of how expensive carrying the errors and measuring error covariance. So if you have observations nearby, there may be covariances of errors associated with them. So inverting the matrices in sequential methods and computing the adjoints and so on in variational approaches can all be very expensive. Okay, so obviously this is a very brief introduction. You will have to read up if you are interested in more details. But data assimilation is a very important part of the forecast system, and it turns out that the ensemble forecast reliability and skill also depend on the data assimilation, how well the system merges the data with the model to produce initial conditions and initial error space for model uncertainty and ensemble spread and so on. Okay.